1.4 Lesson 1, Definite Integrals by Trapezoids from Equations and Data. Our objective for today's lesson is you'll be able to estimate the value of a definite integral by graphing the function and estimating the area under the graph of the function above the horizontal axis between x is equal to a and x is equal to b by using areas of trapezoids. You will remember that in the previous section we did the same thing, but we counted squares instead of using areas of trapezoids. So this is another way you can do that. You can also use rectangles, as we will see later when we get into integral calculus. So vocabulary is the same vocabulary that we had in the previous lesson, definite integral. So for example, if you have the definite integral of negative 1 over 16 x squared plus 12 integrated with respect to x from x is equal to 0 to 8. So this is called a definite integral. The integrand would be the function negative 1 over 16 x squared plus 12. That's the integrand. The lower limit of integration would be 0. The upper limit of integration would be 8. Together, 0 and 8 are called the limits of integration, and in this problem we have integration with respect to x. And as we understand from the previous lesson, you have a product here, and that's why you need to write the dx. So we begin with our first example. Example 1, approximate the definite integral of negative 1 over 16 x squared plus 12 with respect to x from 0 to 8 by using 4 trapezoids of equal heights. So this is an example for definite integrals by trapezoids from an equation. You can see that the integrand is given as an equation. So we want to estimate the value of this definite integral by graphing the function and estimating the area under the graph of the function above the horizontal axis between x is equal to 0 and x is equal to 8 by using the areas of 4 trapezoids of equal heights. So we want to approximate the definite integral of f of x, which is the function that we referenced earlier, negative 1 over 16 x squared plus 12, on the interval from 0 to 8, by using 4 trapezoids of equal heights. So let's begin by graphing the function. So our function is f of x is equal to negative 1 over 16 x squared plus 12, and you can see the graph of the function shown here in black. And what we want is the area. We want to approximate the value of this definite integral, which means the same thing that we worked with in section 1.3. It is the area under the graph of the function f, above the horizontal axis between x is equal to 0 and x is equal to 8. So we're interested in finding the area of the region that I'm about to show. So we want to find the area of this region. And the way we want to do it, as specified in the instructions, is by using the areas of 4 trapezoids of equal heights. So we're going to draw our trapezoids oriented this way. Our trapezoids will be drawn in that orientation. And each trapezoid has a height, and it has 2 bases, base 1 and base 2. And we know the area for a trapezoid is given by this formula, 1/2 times the height times the sum of the lengths of the 2 bases. That is the formula for the area of a trapezoid. It is, again, 1/2 times the height times the sum of the lengths of the 2 bases. So keep that in mind as I draw my trapezoids to fill the region whose area we want to find. So here we begin with our first trapezoid, which has a height of 2 units, Again, if we go back to the instructions for the problem, the instructions state approximate the value of this definite integral by using 4 trapezoids of equal heights. So we'd like for the heights of our 4 trapezoids to be equal, and since our definite integral is going from x is equal to 0 to x is equal to 8, the length of that interval would be 8 minus 0, which would be 8. And if you divide that by 4 trapezoids, the height of each trapezoid would have to be 2 units for the heights of the 4 trapezoids to be equal. And that is why my first trapezoid is drawn on the interval for x from 0 to 2, so that the height of my first trapezoid would be 2 minus 0, or 2 units. And my second trapezoid, I will show that in green. This is my second trapezoid. My third trapezoid, I'll show that in blue. And notice again that the height of each of my trapezoids is 2 units. 4 minus 2 is 2. My third trapezoid, I'll show that in blue. And again, the height of this trapezoid is also 2 units. And my last trapezoid, I will show that in black. And again, you'll see that the height of this trapezoid is also 2 units. So what is it that I need? Well, I need to find the area of each trapezoid. And how will I do that? By using this formula for the area of a trapezoid. It is 1/2 times the height times the sum of the lengths of the 2 bases. So if you look at our first trapezoid, which is the gold trapezoid, the height is 2 units. All of our 4 trapezoids have the same height of 2 units. And of course, in all of the 4 trapezoids, when you use the formula for the area of a trapezoid, you will have 1/2 times the height. So you will have 1/2 times 2 in all 4 trapezoids. What about the lengths of the 2 bases? Well, let's look at the first trapezoid, the gold one. We have base 1 here, and we have base 2 here. What about the second trapezoid? Well, we have base 1 here, and then we have base 2 here. What about the third trapezoid, the blue one? Well, this would be base 1, and this would be base 2. What about the fourth trapezoid, the black one? That would be base 1 here, and this would be base 2 here. So when we find the area, we're going to do this. So for the first trapezoid, for the gold trapezoid, we're going to write area is equal to 1/2 times the height. The height is 2 units, times the sum of the lengths of the 2 bases, base 1 plus base 2. Now, what is the length of base 1? The length of base 1 is the distance from the x-axis to this point on the graph of the integrand. The integrand is the function f of x. Quite simply, this would be the function f evaluated at x is equal to 0, which is, of course, 12, as we can see from this table. So we're going to have, I'm going to try to be a little bit general here and write f of 0, but we know that to be 12, plus the length of base 2, which would be the height of this vertical line segment, which would be f of 2, which is, of course, 11.75, but I'll write f of 2 for now. And then, if you look at the second trapezoid, we're going to use the same formula for the area of a trapezoid. We're going to have area is equal to 1/2 times the height is 2, times the sum of the lengths of the 2 bases. Base 1 would be the height of this segment that I am now trying to show you by shading green, which is, of course, f of 2. So I'm going to write f of 2, and we know what f of 2 is. It's just the function f evaluated at the input 2, which is 11.75, plus the length of base 2, which would be the green segment that I'm highlighting now, which would simply be f of 4. F of 4. And then the blue trapezoid, which I'm highlighting now, you see this line segment in blue, and you see this line segment in blue. So the area of that trapezoid is equal to 1/2 times the height, which is 2. So we have 1/2 times 2 times the sum of the lengths of the two bases. And then the first base would simply be the length of this blue line segment, which is, of course, the function f evaluated at 4, which would give me f of 4, which I know to be 11. But I'll write f of 4 for now, plus the length of base 2, which would be the function f evaluated at 6, which I know to be 9.75. But I will write f of 6 for now, f of 6. And then the last trapezoid, which I will shade in black, is right here. And I need to find the lengths of these two line segments because they are the lengths of the two bases. So we're going to have area is equal to 1/2 times the height, which is 2, times the sum of the lengths of the two bases. The first base has a length given by the function f evaluated at 6, which is 9.75, but I'll write f of 6 for now, plus the length of the second base is the function f evaluated at 8. So I'll write f of 8, and of course f of 8 is equal to 8. So we have f of 8. So if I do this and I add the areas of the 4 trapezoids, that would give me an approximation. Why is this an approximation? Because the top boundary of the region that we're interested in is actually given by a curve. And for each of our trapezoids, if you look at the top boundary, it's going to be a line segment. Like, for example, here, for the first trapezoid, you have a line segment here. For the second trapezoid, you have a line segment. For the third trapezoid, you have a line segment, and so on. So you're approximating the curve with line segments for each of the 4 trapezoids. And that is why this is going to be an approximate value for the definite integral rather than the exact value. Let's go back to what the problem is asking us to do. Approximate the value of the definite integral of -1/16 x squared plus 12 with respect to x from 0 to 8 by using 4 trapezoids of equal heights. So we're ready to do that. And as we saw with our trapezoids, this is how we find the area of each of our 4 trapezoids. And of course, we can substitute for f of 0 by what f of 0 is. F of 2 is 11.75, f of 4 is 11, f of 6 is 9.75, and f of 8 is 8. And we can make substitutions for those quantities from the output values of our function f. And once we do that, we can just do the arithmetic that's needed and complete our approximation for the value of this definite integral using 4 trapezoids of equal heights. I'd like to show something here that you might be able to see, and you can do this whenever you're using trapezoids of equal heights. So I'm using 4 trapezoids of equal heights in my problem. So you can see that of the 4 areas, I'm adding the areas of the 4 trapezoids together, and you'll see that for each area you always have 1/2 times the height, because that comes from the formula for the area of a trapezoid. So that is actually a common factor that I have from each of my 4 areas. So I can simplify by factoring out 1/2 times the height, which is, of course, 2 in my specific example. And what am I left with? Well, from the first term, which is the area of the first trapezoid, I'm left with f of 0 plus f of 2. And from the second term, which is the area of the second trapezoid, I'm left with f of 2 plus f of 4. And from the third term, which is the area of the third trapezoid, I'm left with f of 4 plus f of 6. And from the fourth term, which is the area of the fourth trapezoid, I'm left with f of 6 plus f of 8. So one thing that you may notice is I have f of 2 twice, I have f of 4 twice, and I have f of 6 twice. And I have f of 0 once and f of 8 once. And the reason for that is the trapezoids themselves. You can see that for the 4 trapezoids that we have here, for the very first trapezoid, base 1 is f of 0. But base 2 is f of 2, which is reused as base 1 in the second trapezoid. So f of 2 appears twice, but f of 0 appears only once for the first trapezoid, and f of 8 appears only once for the last trapezoid. But the other base lengths, they appear twice for 2 trapezoids that are next to each other, that basically share one base as a boundary. So that is the explanation for why you have f of 2 twice here, and f of 4 twice here, and f of 6 twice here, but f of 0 once, and f of 8 only once. So if you wanted to simplify this, you could write 1/2 times 2 times f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6 plus f of 8. And this is called the trapezoidal rule. And you can use the trapezoidal rule whenever you're using trapezoids of equal heights to approximate the value of a definite integral. However, your trapezoids have to be of equal heights for the trapezoidal rule to be used. If your trapezoids have different heights, you cannot use this rule. You would just find the area of each trapezoid using 1/2 times the height times the sum of the lengths of the 2 bases. One other thing you can do is you can take this 1/2 and you can distribute it to each of the terms inside the brackets. And when you do that, 1/2 times 2 will give you 1. So 1/2 times 2 will give you 1 for each of those terms. And 1/2 times f of 0 will be 1/2 times f of 0. And 1/2 times f of 8 will be 1/2 times f of 8. So I have distributed the 1/2, so that's gone. And when you do that, you have the formula for the trapezoidal rule, which is stated as a property in your textbook. So the delta x refers to the height of each trapezoid, which in our example would be 2. And then you have 1/2 times f of a. A is the lower limit of integration, so this is for the definite integral of f of x dx from x is equal to a to x is equal to b. So that's where the a and the b come from. So in our particular example, a is equal to 0 and b is equal to 8. And that is why we have f of 0 here and f of 8 here. And then you just have 1/2 times f of a, and at the very end you have 1/2 times f of b. Just like in our specific example, we have 1/2 times f of 0, and at the very end we had 1/2 times f of 8. And in between, you have the function f evaluated at each of the x values, which are called partition points. They basically partition the interval from 0 to 8 into sub-intervals of equal widths. So now if you want to apply the trapezoidal rule to our problem, this is what you would do. And you can use the trapezoidal rule because what we have is an approximation of this definite integral using 4 trapezoids of equal heights. What is the height of each trapezoid going to be? The width of our interval is 8 units, and we want to divide that into 4 subintervals of equal widths. So the height of each trapezoid will be 2 units. That's the delta x. And then you have 1/2 times f of a. A is 0, so we have 1/2 times f of 0. And then you have plus f of 2. Why is it that I have 2? Because you have the interval from 0 to 8. So here is 0, and here is 8. And you want to divide that into 4 subintervals of equal widths. So when you do that, each subinterval will have a width of 2 units. So this would be 2, this would be 4, and this would be 6. So you have 0, 2, 4, 6, and 8. These are called the partition points of the interval from 0 to 8. And you're going to evaluate the function f at each of those partition points. And you're going to use this formula. And we talked about where this formula comes from. It comes from the formula for finding the area of each trapezoid, and when you add the areas of all of the trapezoids together, you can simplify that sum to make it look like this, as we did earlier. So now you have f of 2 plus f of 4 plus f of 6 plus 1/2 times f of 8. And that would be it. So now we're going to have, that would be equal to 2 times 1/2 times f of 0. And again, what is f of 0? F of 0 is 12. It's the function f evaluated at x is equal to 0, which is, of course, going to be the length of the first base of the first trapezoid. And then you have f of 2 is equal to 11.75, f of 4 is equal to 11, f of 6 is equal to 9.75, and f of 8 is equal to 8. Again, if you want to understand it visually, go back to this particular slide. So f of 0 is 12, f of 2 is 11.75, f of 4 is 11, f of 6 is 9.75 plus 1/2 times f of 8, which is 8. So now you just do the arithmetic, and you would have our approximation for the value of this definite integral. And that would be approximately 85 square units. So what was it that we just did? We just estimated the value of a definite integral by graphing the function and estimating the area under the graph of the function above the horizontal axis between x is equal to a and x is equal to b by using areas of trapezoids. The problem that we just did was the definite integral of negative 1 over 16 x squared plus 12 with respect to x from x is equal to 0 to x is equal to 8, and we approximated the value of that definite integral by using 4 trapezoids of equal heights. Here's a visual representation of the 4 trapezoids. This is what you would have when you add the areas of the 4 trapezoids together. We looked at how we can simplify our calculations by using the trapezoidal rule as long as we are using trapezoids of equal heights. And we applied the trapezoidal rule to our particular problem to approximate the value of our definite integral to be 85 square units. Here's an interesting question for you. Do you think this approximation is greater than the exact value of the definite integral or less than the exact value of the definite integral? And to help you think about that, look at each trapezoid and see if there is some area that's left as a gap between the actual area of the region and the area of the region that we're using to approximate the actual area. So the actual area is under the graph of f of x. above the horizontal axis between x is equal to 0 and x is equal to 8. And for that actual area, we're using the areas of 4 trapezoids to approximate it. So for each trapezoid, you have to think about, is there some overestimation of the actual area or underestimation of the actual area? And that has to do with what we call the concavity of the graph of f. How is it curved? So that the trapezoid, will it be like inside the region or outside of the region? That's basically what you have to think about to answer the question of whether your approximation is an overestimate or an underestimate, and I'll leave that to you to complete the thought. The next example that we want to look at for today's lesson will have to do with definite integrals by trapezoids from data. In the first example that we looked at, the function f of x was defined by the rule -1/16x squared plus 12. So that was an example of definite integrals by trapezoids from an equation when the integrand was defined by an equation. But now we'll look at a problem where we don't have an equation, but instead we will be working with some data that's provided. But our objective remains the same. You'll be able to estimate the value of a definite integral by graphing the function and estimating the area under the graph of the function above the horizontal axis between x is equal to a and x is equal to b by using areas of trapezoids. This is example 2 from the textbook, and it states, on a ship at sea, it is easier to measure how fast you are going than it is to measure how far you have gone. Well, you're in the middle of the ocean, and you don't really have visual markers that you can use to determine how far you've gone. So it is easier to measure how fast you're going than it is to measure how far you've gone. Suppose you're the navigator aboard a super tanker. The velocity of the ship, which is of course a measure of how fast you're going, is measured every 15 minutes and recorded in this table. What do we want to do with this data? We want to estimate the distance the ship has gone between 7:30 p.m. and 9:15 p.m. So we have some data about how fast the ship is going. We know that at 7:30 the ship is going 28 miles per hour. And at 7:45 the ship is going 25 miles per hour. At 8 p.m. the ship is going 20 miles per hour, 8:15, 22 miles per hour, 8:30, 7 miles per hour, 8:45, 10 miles per hour, 9, 21 miles per hour, and 9:15, 26 miles per hour. So we have some data about the velocity of the ship. We began section 1.3 with this graph. The graph shows the velocity of a passenger jet in miles per hour from t is equal to 0 to t is equal to 5 hours. So on the vertical axis we had the velocity of the airplane in miles per hour, and on the horizontal axis we had the time that the plane had been in flight, measured in hours. And we talked about how far the plane traveled from, for example, t is equal to 1 hour to t is equal to 4 hours, or from t is equal to 0 to t is equal to 5 hours. So how do you find the distance traveled by a particular vehicle? So the distance would be equal to the rate multiplied by the time. And of course, sometimes you can have a situation where the rate is not constant, but variable. So we said we can represent that by using calculus as rate, which is velocity, multiplied by the time. And you're going to have the definite integral of the velocity function with respect to time from t is equal to 0 to t is equal to 5, which would be represented by the area of this region under the graph of the velocity function above the horizontal time axis between time is equal to 0 and time is equal to 5. We're going to use the same idea with this problem about our ship. What we will do is we'll take the data from our table and plot it so that the horizontal axis will represent time, just like we had in the airplane problem. We will go from 7:30 to 9:15, And the vertical axis will represent the velocity of the supertanker, just like we had in the airplane problem. And the velocity here will be miles per hour, going from 0 miles per hour all the way to 30 miles per hour. So we'll look at how we plot the data points. The data points are 7:30, 28, so it should be this point here. And then we have 7:45, 25 miles per hour, 8 o'clock, 20 miles per hour. And then we have 8:15, 22 miles per hour, 8:30, 7 miles per hour, 8:45, 10 miles per hour, 9 o'clock, 21 miles per hour, and 9:15, 26 miles per hour. And what do we want to find? The distance the ship has gone between 7:30 and 9:15, which would, of course, just like with the airplane problem, would be represented by a definite integral. Because how do you find distance? It is rate times time. So it's going to be velocity times time, the definite integral of the velocity function with respect to time on the time interval from 7:30 to 9:15. So if you want to call 7:30 t is equal to 0, you can do that. And then so 8:30 would be 1 hour later, and 9:15 would be 1.75 hours later. So you could do that if you want. And then you're just going to find the value of this definite integral. And you can approximate the value of this definite integral by using the trapezoidal rule, because you can see that each of our time intervals are equally spaced. They are all 15 minutes apart, 7:30 to 7:45, 7:45 to 8, and so on. So each of our time intervals are equally spaced. They're all 15 minutes apart, or 1/4 of an hour apart. And what you can do is you can find the area of each of these trapezoids. And we have a number of trapezoids. And each trapezoid will have a height of 0.25 hours, 1/4 of an hour. And what is the formula for the area of a trapezoid? 1/2 times the height times the sum of the lengths of the two bases. And of course, for the first trapezoid that I highlighted in gold, the length of base 1 would be 28 miles per hour, and the length of base 2 would be 25 miles per hour. And the reason why I just wrote the area of the first trapezoid here is I wanted you to understand unit analysis here. So the 0.25 is a measure of time, so that has units of hours. And base 1 is a measure of velocity, which has units of miles per hour. So you have 28 plus 25, and they have units of miles per hour. So when you're finding the area of each trapezoid, you can do unit analysis. Hours and hours will cancel, and the area of each trapezoid will have units of miles representing the total distance traveled by the ship. Why is that? Because distance is equal to rate times time, and we have rate here and we have time here, and when you find the product, you're finding the distance traveled by the supertanker. So you're going to do that for how many trapezoids? 1, 2, 3, 4, 5, 6, 7 trapezoids. But you can of course use the trapezoidal rule because our trapezoids all have the same heights of 0.25 hours. So using the trapezoidal rule, we can see that the value of this definite integral, which would give us an estimate for the distance the ship has traveled between 7:30 and 9:15 p.m., would be approximately equal to, and again, delta x represents the height of each trapezoid, which would be 0.25 hours, times, we will have 1/2 times the function evaluated at 0, which would be the length of this first base, which would be 28 miles per hour. So we have 28 here, plus f of x sub 1, which would be the length of this second base, which would be 25 miles per hour. And you keep continuing with the pattern, plus f of x sub 2 plus f of x sub 3 until you get to the very last one, which would be the length of the second base of the last trapezoid, and you're just going to have 1/2 times that. So the other ones are not multiplied by 1/2. So we have 0 plus 25, and then we have plus 20, and then we have plus 22, plus 7, and then we have plus 10, and then we have plus 21, and then the very last one will be, you will have 1/2 times f of 1.75, or which would be, of course, 26. And again, the reason why we have that is because when you draw your trapezoids, the trapezoids share one of the bases with the trapezoid that's adjacent to it. So for example, if you're looking at this trapezoid here, it's going to share its first base with the trapezoid to its left, and it's going to share its second base with the trapezoid to its right. And that happens for all of the bases except base 1 of the very first trapezoid and base 2 of the very last trapezoid. So that is why you have, again, we talked about where this formula comes from. It comes from 1/2 times the height times the sum of the lengths of the two bases. And what we did was we distributed the 1/2 to the sum that we have for the lengths of the bases. And since some of the bases are doubling, when you multiply 2 by 1/2, you get 1. That's why these are all factors of 1. But there are two bases that are not double, so when you multiply them by 1/2, you just have 1/2 times the length of that base. So that's where that formula comes from, once again. So when you do those calculations, you get 33 miles. So what is the approximate distance the ship has gone between 7:30 and 9:15 p.m.? It would be approximately 33 miles. And there's the approximate symbol, approximately equal to symbol. So in today's lesson, we looked at definite integrals by trapezoids from equations and data, and the example that we just looked at now, we had some data and we were able to estimate the value of a definite integral which represented the distance traveled by the supertanker by looking at trapezoids, which would give us an approximation for the value of the definite integral of the velocity function with respect to time from time is equal to a to time is equal to b. So we were able to approximate the value of a definite integral by graphing the function and estimating area under the graph of the function above the horizontal axis between x is equal to a and x is equal to b by using areas of trapezoids. And when you have trapezoids of equal heights, you can simplify the calculations by using the trapezoidal rule. And we looked at how that came about.